Good day to all of you. I'm Goutam from Electrical Engineering Department, Haldia Institute of Technology. Today my topic is rotating magnetic field of three-phase induction machine. This is a very important portion where all the electromechanical devices which are operated on electromagnetic energy conversion process, they are working with the help of magnetic field, and that magnetic field in a rotating machine they use most of the cases rotating magnetic field with that concept. Okay, so today I want to represent first of all how in case of three-phase induction machine that rotating magnetic field operate. Okay, so first in case of three-phase induction machine, go through this picture. This is the stator part of that three-phase induction machine, and in that stator part, because it is a three-phase induction machine, it is having three-phase distributed winding. Okay, where R phase is there, R dash, one is entering current, one is exiting, 120 degree apart with respect to R phase. There is a Y phase, Y and Y dash. Again, third phase, B phase, that is again B and B dash with respect to Y, that is also 120 degree electrically apart, that is B and B dash. Okay, similarly this distributed three-phase winding, this picture is for two-pole system. Now if you consider these three-phase winding, they are having a current, R phase having R phase current, Y phase having Y phase current, B phase having B phase current, and these currents are also 120 degree apart. Okay, and this stator having a single core where this is a circle in nature. Okay, so all the magnetic field, all these magnetic fields, R phase, Y phase, B phase, these current create flux. R phase create R phase flux, Y phase flux, B phase current, B phase flux, and all these currents creating individual fluxes, and these all fluxes moving in the same core, in a circular, the same core. Okay, and because of that circular stator core, in that three-phase induction machine there is a generation of rotating magnetic field. In short, we are saying that is RMF. Okay, so now we try to understand how that RMF generate. Okay, first of all I took these three individual phases, their current distribution and corresponding their flux distribution. So this is three-phase waveform, current waveform, and this current waveform will generate three-phase flux. Okay, so that red color represent the sinusoidal waveform of R phase flux, Y represent Y phase flux, B represent B phase flux. Okay, to understand the RMF, we try to represent three different time instant, and on these time particular instances we try to understand what are the resultant flux distribution. Okay, so first of all we consider that at time t1, when we consider these are the current expression. IR stands for Im sin omega t, Iy stands for Im sin omega t minus 2 pi by 3, and Ib stands for Im sin omega t plus 2 pi by 3. Hence all these current waveforms are 120 degree apart, and at t1 time instant, putting omega equals to 0 degree, we got the expression of currents for that time instant t1, that is equal to IR equals to 0, Iy equals to minus of 0.866 Im, Ib also 0.866 Im. Okay, these current will generate corresponding fluxes. IR create phi R flux, Iy create phi Y flux, and so on. Okay, so their magnitude also phi R equals to 0, phi Y equals to 0.866 phi M minus, and phi B, that is equals to 0.866 phi M plus. Okay, Now if you understand these magnitude, how these fluxes for that particular instant, how they react on that instant and creating the resultant flux, to understand that we can go for Fleming's thumb rule. Okay, according to that, this plus sign, dot sign, or sometimes it is cross dot like this. So according to that, we normally consider that dot means current is coming out and cross means current is entering. So with that concept, if we move in that direction, if we pick our hand, right hand, the direction of thumb representing the direction of current, okay, and the direction of other fingers representing the direction of, due to that current, generation of flux. Okay, so using that we try to find out for that what is the amount of flux generation in which direction. Okay, now if you can split that three different phases, their current contribution as well as flux contribution, the R phase representing in that portion which is phi R, due to that tangent means perpendicular to that R phase, there is R phase flux. Okay, because that phi R is equals to 0, I am showing the direction but the magnitude remains same, 0. Okay, whereas considering here with this kind of thumb, right hand thumb rule, we try to represent the direction of flux in Y phase. Okay, that is again 0.866, and the direction, because I provide the direction here, the minus sign signifies the minus here or dot, and plus sign or cross sign signifies the cross, means the current is entering, and the minus representing the current is coming out. So taking that concept, I got the direction of flux in Y phase downward towards that direction according to this direction provided. Similarly, B phase, because the flux phi m is positive, so and IM also IB also positive, so taking this side B side plus and B dash as a minus, taking that consideration, using again right hand thumb rule, I find the direction of flux, that is again downward, perpendicular with respect to that B phase downward, and that magnitude is again 0.866 phi m. So if we consider at time t1 time instant, the contribution of overall flux, that can be the combination of R phase flux, B phase flux and Y phase flux. Okay, so I need to sum up all these three components of flux for that time instant, t1 time instant. Okay, so if I add them up, R phase flux is 0, Y phase flux is 0.866 downward this direction, and B phase flux contribution is again downward towards that direction. To represent that, the resultant flux is actually the 0.866 phi m downward towards that direction. Again, this is for B phase flux representing by blue color, that is again downward towards that, and their resultant will be this green color, which is represented as phi t1. Okay, that phi t1 is downward represented by that green color. Okay, that phi t1, that is the combination of Y phase flux and combination of B phase flux. If we add up with their phases sum, we find the, with respect to the phi tm direction, the contribution of Y phase, this angle is 30 degree. Similarly, with respect to the B phase contribution towards that phi tm direction, downward direction, that is also 30 degree. Okay, why that is 30 degree? If you want to understand, that can be represented like if you draw the phasor diagram, phase distribution, this is the direction of R phase, which is the direction of Y phase, and this is the direction of B phase. They are 120 degree apart. R phase with respect to the Y phase 120 degree apart. Okay, now if we consider, it will generate I took different color. If it will generate with respect to that the flux which is okay, so the three phase suppose if R phase is there, R phase value is 0, so Y phase, in case of Y phase axis is towards that direction. So if it generates flux, that flux distribution is towards this. Okay, now if this angle is 120 degree, now it generates a flux that is again 90 degree with respect to this, so this is 90 degree. Okay, so in total, if we consider by the contribution of Y phase, that total angle is 120 plus that 90 degree. Okay, so that means it will be 210 degree. Okay, whereas that green color means phi t1 means resultant flux at t1 time instant, that is downward direction, towards that direction. Okay, so this is 180 degree. Okay, so this angle with respect to phi t1, the Y phase displacement, flux displacement is actually we are getting 30. Okay, so this 30 degree we will present over here. So the contribution of Y phase flux, that is cos 30 degree of this phi, this portion. Okay, so that is the contribution of Y phase flux toward downward direction. Okay, next if we go for the other phase, if we go for that same thing, in this picture also the contribution of flux can be represented by this term, Y phase flux. Okay, similarly contribution of B phase flux, if you want to find out, the B phase axis is towards that. Okay, so with respect to that, the contribution of flux perpendicular with respect to that is towards this direction. Okay, now if this is 120 degree, then its contribution, flux contribution is 90 degree with respect to that. So this is 90 degree, this one 120 degree. So overall, this total flux contribution, that is 120 degree plus the 90 degree from this side. Okay, whereas the the resultant flux direction, that is towards that is downward. So with respect to that resultant flux phi t1, the difference from B phase, that angle is, again we got, this angle is 180 degree, this is 180 degree, and this much is 210 total. So we got actually here also 30 degree difference. So here for B phase we put this 30 degree contribution of flux towards that direction, towards the downward direction is phi b. Because of that, total that expression is this much. Okay, so if we add up all these, we got the expression of resultant flux. The resultant flux expression, that is, if you add up, we got 1.5 times of phi m for that particular time instant, t1 time instant. Okay, so if we find out that t1 instant, then we try to find out next time instant. Suppose we took the next time instant, t2 time instant, that is omega t equals to 90 degree. Okay, now if it is omega t equals to 90 degree, that means for that 90 degree here, instead of this omega t, we will put omega t equals to 90. So sine 90. So sine 90 equal to, we find 1. Okay, here also we put sine 90, and sine omega t, that portion 90, omega t this portion 90. So we got the expression of current like these. Okay, corresponding their contribution for generation of flux will be like this. Okay, that means R phase flux, that is phi m, Y phase flux minus of 0.5 phi m, and B phase flux also minus of 0.5 phi m. Okay, now again like the previous case, this is the flux stator portion, winding distribution, and because of that winding, R phase, that is along that axis, R phase is present along that axis, so its contribution will be towards that direction. Contribution of B phase will be towards that direction. Okay, and contribution of white phase, yellow phase, that is with respect to that yellow phase perpendicular, that is towards that direction. Okay, so if we again add up these three contribution with their proper magnitude, we got the R phase, because it is positive, we do R equals to positive and R dash is minus. Similarly, Y phase, because it is minus, phi m is minus, so we took here minus, here the plus. Similarly, B phase also, that is minus, so here it is minus, so B dash also plus. Okay, so here the minus sign and plus sign we are considering for choosing the direction of current, and also with respect to that the nature of the flux. Okay, in which way the direction of flux will be there. Axis is known to us, but the direction downward or upward, for that thing we go for the sign, minus sign or plus sign. Okay, now for this particular instant we got that three different phases currents are present. Okay, not zero, non-zero items, and their contribution is there. Okay, so if we split them step by step, we find that three fluxes are there. First, R phase flux with respect to this is the R phase. For R phase, this is R phase axis. Okay, with respect to that, direction of flux is perpendicular with respect to that, towards that direction. Similarly, Y phase is towards that axis. Y phase is towards that axis, so perpendicular with respect to that, that is phi y, that is 0.5 phi m. Okay, because I choose the direction for that minus sign or plus sign, I here only took the magnitude only. Okay, means that minus sign and plus sign considered by the direction of flux, either downward or upward. Okay, if it is minus, then here minus, B, y is minus, y dash is cross. Again B also, because it is minus, this is minus, this B is minus, B dash is plus. Okay, so that thing, minus sign, plus sign, we choose according to that dot and cross or minus and plus sign. And with respect to that, again we use perpendicular direction downward for that direction of y phase flux. Okay, and B phase, because this is minus, this one plus, here we consider again this right hand thumb by this. Okay, and for that we got the direction of flux upward. Here also 0.5, here also 0.5. So if we add again three fluxes, we are saying we got a resultant flux. That resultant flux is phi T2. Okay, that is the combination of phi R, phi Y and phi B. So these three fluxes contribution. So if we find out the resultant flux direction will be this yellow color portion, and that is from my right to left towards that direction. Okay, and that case we got the direction of resultant flux. For that we need to find out R phase direction of flux towards that direction, the same direction. Y phase is flowing, representing in that direction, so we need to find out the contribution of Y phase towards this direction. Similarly, contribution of B phase towards that direction. Okay, so to find out that, we took phi M for the R phase. Okay, phi Y, that contribution is cos 60 degree, because Y phase, this angle is, it will create, for this omega t equals to 90, for that it will create 60 degree with respect to that resultant flux phi T2, and the magnitude of that Y phase flux is phi m, 0.55. Okay, similarly if you go for B phase, the B phase magnitude is 0.55 m, so that value, and here it is creating 60 degree with respect to the resultant phi T2. Okay, so its cos component 60 degree and the magnitude 0.55 m. So if we calculate that properly, again we got that magnitude of resultant flux is 1.5 times of phi m. Phi m is the maximum flux. Okay, but in this case we got the resultant direction of flux, that is phi T2, that is phi T2, that is towards that direction. Okay, but that means the magnitude remains same, whereas the direction changes for that T2 time instant. Okay, now if we go for next time instant, what is happening here? In this case, instead of first step is T1, second step is T2, third step we take like this after 180 degree later, where we took omega t equals to 180 degree. So at 180 degree, putting all these value here in this expression, we find IR again becomes 0, IY become 0.866 IM, maximum value of current, and IB is again minus 0.866 of IM. Here again minus we are getting, but other twos are plus. So their contribution is IM here, IR, IY and IB. Okay, their contributions are there. First two, R phase current is 0, so that R phase current is 0. So here with respect to R phase, here because it is 0, I am not providing the direction plus or minus whatever, no sign is there. If it is there, then the direction of flux will be towards that, but the value is 0. So I took phi r 0. Now phi y, for that it is 0.866 phi m, so magnitude is positive, so here I took positive, and on other side is minus. Okay, so because of that, again using my right hand thumb rule like this, and I got the direction of their contributing fluxes, that is upward direction 0.866 phi m. Similarly, go for B phase. B phase here, because it is minus sign, because the minus sign, B phase is minus. Okay, so B phase is minus means B dash will be opposite of minus, that means plus. Okay, so plus means therefrom I will took the direction of flux will be upward. This is my forefinger that is pointing outward, that is from that minus, and other thumb representing the direction of flux. Okay, again here I am not mentioning the sign because I already took the sign in that minus and plus. Okay, so in that case, if we sum up again, we have the three fluxes where the R phase value is 0. So if we add sum of Y phase and B phase, that is Y phase flux, B phase flux, if we add sum up, then again we got the expression of Y phase is towards that, .865 m, and opposite is .8665 m. So the resultant will be upward direction. Okay, the resultant will be phi t 3, that will be upward direction like this. So here if we have the resultant flux, the resultant flux will be this, their contribution is Y phase flux towards that phi t3 direction, that will be this much of angle. Again if you calculate like the first t1 time instant, this angle again will be 30 degree. Again same like the t1 time instant, this angle also it will create 30 degree. Okay, so if it is 30 degree, so Y phase flux towards that direction contribution is cos 30 degree with this magnitude. Okay, with this magnitude, so that resultant value is this, and similarly B phase also cos 30 degree into the magnitude. So if you add all of them, we got the expression is this expression is a mistake, that is 1.5 times of phi m. Okay, so we try to find out three different time instant, t1, t2, t3. These three time instances, the contribution of flux and the direction of flux, we find for all these three different time instances, we find at t1's time instant where the omega t equals to 0, that time instant the resultant flux is, we are saying, that is phi t1, means flux generated, resultant flux generated due to t1 time instant, that is downward, and that magnitude is 1.5 times of phi m, 1.5 times of phi m. Okay, downward direction. Phi t2 means after 90 degree later, the direction of resultant flux is again 1.5 times of phi m, right to left, and at 3 time instances is after 180 degree later, with respect to this 180 degree later, again we got that magnitude of flux, that is 1.5 times of phi n. Okay, that means 3 different time instances, 90 degree later time instances, we find that magnitude of flux remain constant, whereas the direction of flux is getting changes. Okay, so if we keep on checking all these things, we next instance we will find the direction of flux will be maybe towards that direction, next instance is toward that. Is if we take continuously different time instances, we find different, means the nature will follow like this. Okay, where it seems to have the flux, resultant flux is continuously rotating in the continuous time frame. Okay, and we know if the, with respect to that magnetic field, if the rotor follow that magnetic field and it tried to orient towards the direction, and it also tried to orient itself towards that magnetic field, and it also like this, it also tried to rotate itself in a same direction like this rotating magnetic field. Okay, this is known as rotating magnetic field, where we observe for 3 different time instances we find the flux is there and their magnitude remain constant, whereas the direction time to time changing in a particular direction. For this kind of R, Y, B phases, their flux distribution is continuously representing, the orientation is clockwise. So if the rotating magnetic field is moving, the magnetic field is there, that is moving in a clockwise direction with this kind of phase sequences, R, Y, B, 120 degree apart phase sequence, it continues to rotate in a clockwise direction. So that is called RMF. Because of that RMF, rotating magnetic field, the induction motion also will experience electromagnetic induction. With that principle, it tries to rotate, and it will rotate with the speed of this. Okay, with the speed of ns, where that speed of that can be represented by the expression of ns equals to 120 f by p, where f is representing the frequency, linear frequency, p is the number of pole, ns is the synchronous speed. This is represented as synchronous speed, which is equals to 120 f by p, that speed. Okay, so that is known as rotating magnetic field. Okay, we know transformer also having 3-phase winding, it is having a core, but in case of transformer there is little bit different with respect to the rotating machine, where the main thing is that rotating devices having a single rotating circular core. Okay, all 3 phases they are creating fluxes, and the fluxes are moving in the same single circular core. Okay, that is not present in case of transformer, whereas in this rotating machine, stator part, it is having a single circular core. Okay, all R phase, Y phase, B phase, 3 different fluxes are there, and all of them are present in the same magnetic field. All the fluxes contribution is within this same stator core, and because of that, if they are physically 120 degree apart like this in case of 2-pole system, and if electrically the signals are, means within these R phase, Y phase, B phase, their current are also 120 degree apart, then there is a chance of rotating magnetic field. Okay, so that is the main criteria for generation of rotating magnetic field, which is not actually present in case of transformer, where the this portion is not present in case of transformer. In case of three-phase induction machine, we find rotating magnetic field thing. In case of two-phase system also, we can observe rotating magnetic field. For that case, there will be only two phases, but still, because only two phase, still also we also have rotating magnetic field, and because of that machine can rotate, because of that rotating magnetic field. Okay, now we try to understand same rotating magnetic field thing operated in a two-phase machine. In case of two-phase machine, what is there? There is only two type of winding. Okay, and where that one of the phase is placed like this, one of the phase is placed like this, and other phase is placed 90 degree with respect to that. Okay, so if we want to find out that first phase, that is green color, towards that axis, and with respect to that 90 degree apart, second phase. Okay, and their corresponding current contribution also, they are also 90 degree apart. Okay, and again they are placed in a single stator core, circular core, where both the fluxes, means first phase creating a flux, that flux also rotating present in this stator core, second phase also creating another part flux, that also present in a same core. So if both of the flux combine together, they will create resultant flux, and that resultant flux we try to understand for different, again three different time instances, how they are contributing. And again we find there also there is a generation of RMF, rotating magnetic field. Means we try to understand that in three different time instances their magnitudes are remain same, but their direction changes time to time. Okay, so in case of two-phase system, generation of RMF, which is actually responsible for creating the machine to rotate. Okay, now for that first case, we consider the first phase like ID, name is ID, that is equals to In sin omega t, and IQ, that is equals to In sin omega t minus pi by 2, 90 degree apart. So for that time instant t1, putting that t1 equals to omega t equals to 0 degree. So for that, putting those value, we find the magnitude of ID will be 0, magnitude of IQ will be omega t equals to 0, that means sin minus 90, so that is minus of Im. So that means we are getting the corresponding, because that IQ equals to minus of Im, so phi q also will be minus of phi m. Okay, so as it is minus of Im, so this side q equal to minus, this is plus, q dash equals to plus. Okay, and because of that, again use right hand thumb, the direction of resultant flux will be along the downward direction, and for that instant we are getting a flux, that is phi t1, which is downward direction, and the magnitude is phi m. Okay, which is contributed by q axis current. Okay, now next, if you go for next time instant, suppose t2 time instant, where this time instant where omega t we consider as the ID degree, putting here omega t equals to 90, we got that ID equals to Im, whereas IQ equals to 0. So ID corresponds to ID also phi m, and IQ corresponds to creating phi q, that is also 0. So because that ID is present, IQ will be there, phi d will be there, and the direction of phi d, because it is positive, so this is plus sign, d first plus sign, opposite of that d dash, that will be minus sign, again that contribution like this towards that direction of flux, because of the direct d axis towards that direction. So resultant flux, again we got phi m, this amount towards that direction. Okay, so phi m amount, like the previous one, downward direction phi m, resultant flux was downward and the magnitude was phi m. Now we got right to left, magnitude remains same, phi m. Okay, now if we go for the third instance T3, for that T3 omega d equals to 180 degree, and when that omega d equals to 180 degree, for that phi d equals to I d equals to 0, because that 180 degree sine 0, it is 180 degree sine 180 degree equals to 0, so that I d equal to 0, whereas IQ will be Im. Okay, so corresponding IQ actually responsible for creating phi q, which is phi m. Okay, so for that particular instance, T3 time instance, we got that resultant flux is outward direction, and that is magnitude is again phi m. So in that two-phase system, we find that three different time instances, we find three different resultant flux. T1 time instant, downward direction. Next time instant, it will move clockwise 90 degree. Next third time instant, again it move again 90 degree. So if we keep on checking different time instances, we find that there is a flux, and that flux magnitude remains same, and that is continuously rotating, in this case clockwise direction, and that magnitude is phi m, and it is rotating clockwise direction. So that is rotating magnetic field in case of two-phase system. Okay, so that is two-phase system for that rotating magnetic field, and because of that there is a speed continuously generated, and that speed again expression is ns, that ns equals to synchronous speed, that is equals to 120 f by t, like the first case. And because of that magnetic field, there will be a electromagnetic induction, and because of that rotor will experience that force, and it continues to rotate in that direction according to the electromagnetic induction principle. So this much